Rarely have I begun a talk by correcting scurrilous mistruths, but it is neither true that I play ukulele nor that I play it well. However, I have been trying to learn how to play guitar, and I will in fact be emceeing a ukulele fest. So there you go. It's mostly true. So I'm going to talk today about two views of the human mind. One is, don't touch that dial, the human mind is perfectly adjusted, which is maybe a variation on Leslie Orgul's saying that nature is cleverer than you are. And which I think is widespread in the popular literature on at least evolutionary psychology, and another view which says maybe there's still room for improvement in the human mind. The first is, I think, well captured going to classical sources, among others, William Shakespeare. What a piece of work is man, how noble in reason, how infinite in faculty. And you see a lot of echoes of this in contemporary cognitive science. For example, Pinker's book, How the Mind Works, starts with an extended discussion of how well human vision works, and then says if the parts of the mind that allow us to see are indeed well engineered, there's no reason to think that the quality of engineering progressively deteriorates as the information flows upstream to the faculties that interpret and act on what we see. I want to suggest there are some reasons to be concerned about what happens upstream. Noam Chomsky recently has been arguing that language appears to be surprisingly perfect, coming close to what some super engineer would construct given the conditions that the language faculty must satisfy. And you've already heard some discussion of Bayesian decision theory, more in the context of artificial intelligence, but the notion is that notion in cognitive science recently, is that human beings might be basically Bayesian reasoners that make optimal inferences given some set of priors and some set of data. There are also lots of evolutionary psychology papers like this one that just came out in Psychological Review, which says the bright side of being blue, depression as an adaptation for analyzing complex problems. So there's a kind of common theme in evolutionary psychology which we might call it's not a bug, it's a feature. And I'm not here to challenge the notion that some of the things that look like bugs are features, but I want to suggest that we shouldn't assume that as a default. The reason that a lot of people are optimistic about the human mind, those who are, often has something to do with evolution. So a common metaphor for evolution that I'll mention briefly in a moment is hill climbing. And here's a quote from John Tooby and Leda Cosmides, who most people view as the founders of evolutionary psychology. And here's what they say. Because natural selection is a hill climbing process that tends to choose the best of the variant designs that actually appear, and because of the immense numbers of alternatives that appear over the vast expanse of evolutionary time, natural selection tends to cause the accumulation of superlatively well-engineered functional designs. And yet, as Groucho Marx said, who are you going to believe, me or your own eyes? There are some conspicuous exceptions. I gave this talk to a bunch of business people the other day, and it almost seemed as if they didn't remember the guy on the left anymore. I'm glad that this still gets at least a little residual laugh. Of course, it's not just the guy on the left, but, for example, a lot of Republican voters went from, or rather continued to believe even after we'd invaded Iraq that there were weapons of mass destruction there. Now, of course, the evidence of absence is not the absence of evidence, so you might think they're in some way licensed. But the Bayesian analysis would be to say, what is the distribution of possibilities of having weapons destruction given the available evidence? And would probably come to the conclusion that it was not very likely. Probably many of you know some of the literature by Kahneman and Tversky and people after, showing that there appear to be some limitations in human reasoning, and I think that probably fits with your ordinary intuitions. So that leaves us with a bit of a puzzle. How do we reconcile the supposed power of evolution with the manifest occasional clumsiness of the human mind? Well, the first issue, I think, is with the way that Pinker sets up the argument. He says, well, if vision is well adapted, why should we think that as we go upstream to, say, language or deliberate reasoning, that there would be any issues there? But there's a big issue, which is time. So the brain systems that are responsible for vision and controlling our muscles and so forth are hundreds of millions of years old. The brain systems that are responsible for things like conscious reasoning and language are probably more on the order of a few 100,000 years old. So what's new, of course, may not yet be fully debugged. I think there are a lot of software engineers in the room who know what I'm talking about. The second issue, the second reason that we should be skeptical when we see arguments that assume a superlative evolution is the evolutionary landscape itself. So the common metaphor is climbing, is doing some kind of hill climbing as captured in Richard Dawkins' title, Climbing Mount Improbable. And the idea is that if you take small steps, you sometimes go up, you never go down, and most of the time you just stay where you are. Eventually you make it to the top of the mountain. So Mount Fuji is there on the right, and you can imagine some hill climbers following that method. It might take them a while to get to the top, but eventually they would. And the idea is that the top of the mountain is the kind of optimality we might see. The problem is that the fitness landscape is really a function of a complicated mapping between the 25,000 genes that we have and the trillions of cells in our body. And so, it's probably a better metaphor if you want to think about hill climbing, to think about something like the Himalayas, where it's possible easily to get stuck on some peak that is very short from the highest possible peak that you could imagine. So you might get stuck below the snow line and be in a position where if you take small steps and never go down, you're at what we call a local maximum. And there are lots of examples in human biology. My favorite one is the human spine. The human spine is an okay design, but not a very good design. It's one that any right-thinking engineer would dismiss very quickly. We have a single column that supports 70% of our body weight. And the problem is that a single column is something like a flagpole. Flagpoles are good for holding up light little pieces of cloth that flop in the breeze, and not so good for holding our bodies. An engineer might call it a kludge. It's clumsy, it's inelegant, it gets the job done, so we are upright, we can use tools. It's a lot better than nothing, at least for the kind of niche that we live in, but it's not ideal either. Just to cement the concept in your mind, here's my favorite example of a kludge from the last few years. Gets the job done. This young man was able to air condition his car, but it probably wasn't the most elegant ride on campus. Might not have been good for mate selection. The key point is that our extant biology, what we see around us, is a product not just of adaptive pressure. So I don't want to deny that there is adaptive pressure and that that's a major contributor to the structure of biology, but it's not just adaptive pressure. There are also things like evolutionary inertia, the history of an organism that lead to its design. So I'm borrowing the term evolutionary inertia from Newton, of course. Physical inertia is an object that's at rest tends to stay at rest. An object that's in motion tends to continue in motion. You can think of evolutionary systems in the same way. Once evolution goes in a particular direction, other things being equal, it is more statistically probable that new forms will be small modifications of old forms. This is what Darwin called descent with modification. So why do we have a single column spine even though maybe 3 columns in a tripod form or 4 columns and shock absorbers or something like that, like in a car, might work better? Why do we have the single column design? Because it's cheap in evolutionary terms, and evolution is very stingy. It tends to make modifications of a small number of genes. That's not a conscious process, but the more genes that you would need simultaneously to change, the less probable any particular evolutionary thing might be. And so, as Francois Jacob put it, evolution is like a tinkerer. Evolution is not an optimizer, but a tinkerer. Where this talk in my recent book comes in is asking the question, well, is the human mind a kludge? So I don't think any evolutionary biologist would seriously doubt that biological structure is often kludgy. It's not always. Sometimes it's pretty close to optimal, but frequently it is. Well, what about the human mind? I think sociologically, evolutionary psychologists haven't really considered this question that much. They focused on the cases where there are apparent bugs that could be argued to be features, and I thought it would be worthwhile to look at some other cases. I only have time for one today, but I'm focusing on one that I think is really pervasive, really fundamentally changes the texture of human cognition, which is memory. So you could come up with a long list of design criteria for what an optimal memory system might be, but we could start with things like this. It would be able to encode information on a single exposure. It would avoid blending together distinct memories. You put something in, you expect to get out the same thing. And it will allow systematic searches of data. Of course, my iPhone can do all of that, as can any digital computer, but my brain can't. And I think it's an interesting question. Why? Lots of things that would be trivial for a machine are really difficult for us. So one would be, where did I put my keys? Another would be, where did I put my car? What tends to happen is that we get statistical distribution. So when you want to know, where did I put my keys, what your brain responds with is kind of the distribution of where you tend to put your keys in general. And what you want is really just the last piece of information. Where did I put it most recently? For a computer, that's trivial. You have a buffer, you update the buffer each time you relocate the keys, and there's never a problem. But for us, the memories blend together. This leads to the sad tale at the bottom of the slide, but I'll pause briefly. In your booklet for the conference, you'll see a reference to a piece by Atul Gawande on checklists in the medical profession. So checklists, he argues, can save, I didn't get to refresh my memory, but can save many, many lives and millions of dollars. The point is that a properly engineered memory system would have checklists built in so the surgeons could make sure they've done each proper procedure. And pilots all know this. They realize that they might forget on any particular occasion to pull up the landing gear or what have you, because memories bleed together. That's why pilots need checklists. So this rather frightening fact at the bottom concerns another group of people that have the same problem of memories blending together but don't have the opportunity to use checklists, which are skydivers. So they need to do things a bunch of times, and sometimes the memories might bleed together. You might think that you've pulled the ripcord today because you did it 67 other times, and it turns out that a certain portion of all skydiving fatalities can be attributed to actually forgetting to pull the cord. You might wonder how they know that number. They exclude people that didn't bring a pack at all, the pack was broken, and so forth. So in computers, probably 80% of you are familiar with this, but for those who aren't, the basic organization in a computer is that every single piece of information is assigned a specific location. So you could think of individual memories as like post office boxes or safe deposit boxes. Once something is put in there, it stays there. It doesn't get confused with what's in a different box and so forth. Once you store a number in your address book, it stays there indefinitely. And biological memory just doesn't do any of this. For example, infrequent items are hard to remember. Things that are highly similar, like what you had for breakfast yesterday and the day before, tend to bleed together. There's a typo here. Biological memory is often deeply unsystematic, driven by idiosyncratic and irrelevant contextual information. So, for example, you're all sitting down now. Sitting down will become a cue that can help you remember this very lecture. If you were lying down, you wouldn't remember it quite as well. So there are these sort of arbitrary cues govern how well we remember things. So if computer memory is very well engineered, ours is sort of more like a shoebox where almost everything important seems to go in there. The problem is really on retrieval. We don't seem to have a fundamental problem with encoding. We can encode what we want, but we can't remember things unless we have the right cues, and sometimes it's kind of sloppy. Why do we have this kind of system? I would argue it's not because it's optimal in any particular way, but simply because it's evolutionarily ancient. There might even be an optimal compromise that would be a hybrid of what machines have and what we have that would give you at least some checklist memory, for example. But what we have is a system that's around simply because it's been around for a really long time, and evolution likes to work with off-the-shelf parts. So cue-dependent memory, which is how our memory works, is something you can find in every species, from flies to snails to rodents to monkeys and so forth. So it's a way in which our minds have been shaped by evolutionary inertia. An engineer that was designing an intelligent creature from scratch would not use cue-dependent memory, or at least would not do it without location addressable memory as an underlying substrate. So we wind up with a memory system that's good at central tendencies but lousy at specifics, which is not so good, at least for modern humans. What I want to suggest now is that simple sort of basic commitments, as it were, of course they're not consciously made, can have far-ranging consequences. So consider, for example, framing effects. You've probably heard of these things, like the death tax versus the estate tax. So when the notion of taxing inheritance was called the estate tax, then I think 70% of Americans were for it, and then it was simply relabeled as the death tax, and suddenly 70% of Americans were against it. Or you can think about a soap that's 99% pure, and you're ready to buy two. You think it's practically organic, and then you meditate for a second and think, maybe does that mean it's 1% toxic? And you're tempted to put it back on the shelf. So the question is, why do these effects exist? These framing effects exist. And I would argue that it's an example of what computer scientists would call garbage in, garbage out. Our deliberate reasoning systems are relatively capable of reasoning. I call them deliberate rather than rational, because I think rational would be too strong. But they're only as good as the data that they can summon, and we don't have systematic search. So when we reason about any particular topic, like a tax that's under proposal, the data that we summon we get by matches. So a particular set of cues match and retrieve a particular set of things. If you think about a death tax, you don't go to the same place in your brain as you would go for estate tax. You go to the places where you think about death and taxes, which are the two worst things you can possibly imagine, and you decide that this must be a complete rip-off. It's a phenomenon of memory, ultimately. A similar example is confirmation bias, which is something that bedevils scientific reasoning, but also just everyday reasoning. And this is the idea that we notice evidence that's consistent with whatever particular theories we have, and we're not as good at noticing evidence that's inconsistent with theories. What that does over time is it leads us all to think that each of us individually is the only person in the world that knows anything, and everybody else is incorrect, because we always think about the evidence that supports our theories and not anybody else's. Ultimately, this leads to things like political violence, religious clash, and so forth. Again, I would trace it fundamentally to the dynamics of memory. because the way that priming in memory works, consumer choices are affected. So you see a sign that says limit 12 cans of soup, and you don't want 12, but you start at 12 and you say, I don't need 11, I don't really even need 10 or 9, and you walk away with 8 cans of soup. And that's because the way memory has set up the problem for you. The one on the right is an interesting study of children and their dietary preferences with respect to asparagus and how it is wrapped. Then are personal choices. So this comes from an actual billboard. There is no scientific data on this billboard. I've probably shown it as much as the law firm in question, but there's a similar study in which people were simply asked, would you like to buy a car? And it turned out that people who were asked whether they'd like to buy a car were more likely in the next 6 months to do so. So you can wonder about the consequences of that sign. Yet another example, a very distant example, yet driven by the same thing, is mental illness. So I don't want to say that mental illness is solely a product of the strange way in which our memory is configured, but I think you can see the consequences of memory even in mental illness. So for example, in depression, people get into what I like to call ruminative cycles, where they think about the same negative things over and over again. Well, one set of negative things primes another. If we had systematic search, then you might be able to get some balance, and that's what part of cognitive therapy is about, is getting patients to try to retrieve a balanced sample of data from their own memories. But other things being equal, because we have cue-driven memory rather than location-addressable memory, the stuff that we think about at any given moment is heavily driven by what happened in the last few minutes, and you wind up with these cycles. Same thing in paranoia. The bottom line is this. If our dials were perfectly adjusted, then any change to the human brain or genome would be counterproductive. And when I first circulated this book manuscript, the reaction I got was indeed Leslie Orgel's law about nature is cleverer than you are. There's a kind of notion that we shouldn't mess with nature. But I think a more realistic picture is nature is going to be better at us for some things and not for others. So I've emphasized today some of the things we can't do very well as human reasoners, but there's some things like vision that have been shaped for a very long time where humans are still at least a little bit ahead of the robocars, if not for long. In reality, the current state of human biology is an accidental compromise, as all evolution is, between what would be ideal from a functional standpoint and what was close by at any given point in the evolutionary landscape. Human cognitive architecture evolved relatively recently, so especially when we think about the things that are sort of most essential to defining ourselves, like deliberate reasoning and justice, those are the things that have probably most been shaped by evolutionary inertia. There's the longest history of other organisms on which they're built and the least time for debugging. So that means that there's room for improvement. We can think about how to build machines that are smarter than people, but we can also think about how to build machines that will make people themselves smarter. The architecture of memory might be an especially good place to start. Thank you very much. Happy to take questions.
Hello. Your example on memory and its deficits is compelling, except for the counterexamples that I'm familiar with, where you have human freaks with the ability to, or in fact the curse of remembering every single thing they ever did minute by minute. If they're able to do it, that means it must be relatively close to sort of in there already. And so why is it so far away?
I almost feel like this is a trap because as it happens, I have studied one of those people. So I interviewed somebody who was billed as having this sort of memory for Wired magazine. You can look it up on the web a few months ago. And the person's name is Jill Price, and she's been in all the major media. And indeed, she can remember very well, not minute by minute, but all the sort of important events on each day in her life, and also sort of CNN headline news kind of things, the main things that happen on a particular day. But ultimately, I think that her memory is not really any different from anybody else. So when I went and I interviewed her, what I did was I brought with me some psychological questionnaires to look at the dynamics of memory. And when you give her fresh material that she doesn't have time to rehearse over and over again, she's really not different from anybody else. And she's vulnerable, for example, to the same kinds of similarity errors. So if you give, in a list of words, you give hammer and screwdriver, she might think she's heard chisel. That's not the exact example, but that sort of thing. So she has the same dynamics of memory as anybody else, but she's obsessed with her own past. And so she has vast quantities of photo albums and archives of videotapes, and she spends most of her time thinking about her own past, and she has different ways of relating different events that have happened in particular days. And so I don't think her memory really is different. I think it's her desire to do it. So it's not really different from somebody else collecting stamps and knowing a lot about the stamps. The one last thing I'll say about that is she herself actually does feel quite sad. I wouldn't describe her as the happiest person. And that's part of why the media liked the story, was this notion that if somebody was better than you in one way, then they would suffer. It turns out that 3 other people have the same disorder as she does, and one of them is a DJ in Cleveland. He seems to be perfectly happy. He just remembers these facts and he throws them into his show. So I don't think there's actually a necessary contingency, unlike in the famous story by Borges, where good memory necessarily leads to sadness.
If I can follow, sorry, just
I think I went so long I should go over to another question.
Okay, you mentioned 2 things that in computers, facts are stored in particular locations, unlike the holographic distributed over many locations in the brain. And you mentioned 2 facts. One, that memory is stored in particular locations, but there's redundant arrays of independent disks when it is actually beneficial in an error correction sense to distribute data. And then also you mentioned that infrequently recalled information is more difficult for humans to remember, but there is also caching in computers, which is a way for infrequently accessed data to be it's advantageous for it to be more difficult to access.
I totally agree that there are advantages of memory caching, and if I had a longer talk, I would have spent more time discussing it, but I sort of alluded to that briefly in that I think that the idea would actually be a hybrid. So a system like Google actually takes the basic notion of location addressability and then it merges with some of the cleverer things that human beings do, like kind of keyword addressing and caching and so forth. So ultimately, I think the way to build either the best human beings or the best machines is to be open to what nature does well and also to be open to what engineers do well and try to synthesize the two, rather than starting from the assumption that one is intrinsically better than the other.
Thank you.
Hi, enjoyed your talk. I feel like none of the evolutionary psychologists that you cited would actually say that their argument is that the human mind is well adapted to the modern world. Certainly that it's well adapted to the challenges we used to face, and that they would simply be urging caution and maybe a small c conservative approach to making changes to the mind. So,
it can't be both, though. I mean, on the one hand, I agree with you that evolutionary psychologists often stress this kind of difference between modern world and ancient world. And at the same time, if you really believe that, then you should be prepared to make changes and not assume that the dials are perfectly adjusted. So I think there's some slippage in the evolutionary psychology arguments. A longer quote that I think I have in my recent book from Tooby and Cosmides starts out by saying, well, although the possibility of inept evolution exists, and then it sort of continues on and says that's not really what we see. What we see is superlative evolution. Ultimately, I think it's a difference in emphasis. So I think that what that literature has mostly emphasized are cases where there's an apparent bug that can in fact be cashed out as a feature. And there really are cases like that. So you stand on the side of a cliff and you think you're going to fall when you're not really, and that makes you back away from the cliff. If you had veridical perception, you might actually stand closer to the cliff and be worse off. So there are plenty of cases, I think, that are really like that. But the way the literature has been structured is it's been much more talking about those cases, the ones that there's at least a decent argument that an apparent bug is a feature, rather than the kinds of cases that I'm talking about today. And the one possible case might be the selection task that Tooby and Cosmides have talked about. We could discuss later. I think I should go over here for the last question.
If you were to create some sort of, obviously this is a bit theoretical, but if you were to create some sort of hybridized system between the queue-based memory that you were discussing and a more computer-like system, what do you think that would do to sensory processing that humans do quite naturally and it tends to work for humans? How do you think that would change the way we work?
I think that's an excellent question. The first place that I would start if I were actually building hardware to do this would be to try to take a system that wouldn't change what we encode, that would sort of trust the inbuilt machinery for what should be encoded. I don't think in the long run you necessarily want to do that, but at least in the short run, I think I wouldn't change all the dials at once. I would start with not what gets encoded, but how it gets encoded. And so I would try to build systems that could supplement whatever is already organized by some kind of location addressability, so that it would be easier in order to retrieve the things that the brain is already deciding are worth encoding. In the long run, one could be, one could wonder whether the brain is doing a perfect job of choosing what to encode, but I'll save that one for another day. Thank you very much.